Hello students, welcome to EPG Pathshala. I am Dr. Savita Yadav from Department of Biophysics, AIIMS. Today I am going to talk on module Introduction and Types of Chromatography from paper Techniques in Molecular Biophysics. So students, let's see what are we going to learn from this module. What is chromatography, history of chromatography, theory of chromatography, and factors affecting the process. Brief introduction of various types of chromatography and their application. Chromatography is a preparative or analytical lab technique used for separation of complex mixtures. Chromatography is routinely used in various fields such as chemistry, physics, medicine, microbiology, and pharmacology. Chromatography was discovered by M.S. Sweat in the beginning of 20th century. Chromatographic word came from Greek meaning color writing, as method was based on the colorful picture of separation of plant pigments. The description of similar separation processes was given by L.S. Palmer in the United States and Darré in Europe, almost 10 years of Sweat. In 1931, Lederer together with Cohen and Winterstein published a paper on purification of xanthophyll from calcium carbonate adsorption column, following the procedure described by M.S. Sweat. In 1952, A.P.J. Martin and R.L.M. Singe at Cambridge University in UK were awarded the Nobel Prize for the discovery of partition chromatography. In late 1970, development of high pressure liquid chromatography and reverse phase liquid chromatography changed the field completely. These techniques improved separation, purification, quantification many folds, and further development in the field added computers and automation which brought convenience for the user. Chromatography is a separation process using adsorption by distributing the component of a mixture between stationary phase and mobile phase. Stationary phase can interact and aid in separation, while mobile phase houses the analyte to be separated. Analyte in the stationary phase are retained for a longer time than those distributed selectively in the mobile phase. Analytes are eluted as their concentration in the mobile phase increases with respect to stationary phase. If an analyte is in equilibrium state between two phases, then the equilibrium constant K can be defined as the ratio of molar concentration of analyte in the stationary phase to the molar concentration of analyte in the mobile phase. This is also known as distribution or partition coefficient. A chromatogram is the pictorial representation of chromatographic separation. The retention time TR is defined as the time between sample loading and detection of an analyte peak at the end of the column. Naturally, each analyte in every sample may have different retention time. The time taken for a mobile phase to pass through the column is called Tm. The retention time TR for each analyte has two components, dead time and adjusted retention time. The free space between matrix particle is called as the void volume, V0 of a column. The Tm is measured as time taken by analyte which does not interact with the stationary phase to elute through the void volume, and its value will be same for all analytes. The second component, the adjusted retention time T-R, is the time stationary phase retains the analyte. It is represented as T-R adjusted retention time is equal to retention time minus dead time. So T-R is equal to TR minus Tm. Another term, retention factor K- is used to describe the migration rate of an analyte in the column. This is also referred as capacity factor, and it can be expressed as K- is equal to TR minus Tm divided by Tm. TR is retention time and Tm is dead time. So if you subtract dead time from the retention time, you get adjusted retention time divided by Tm, that is dead time. The retention factor has no units. Ideally for an analyte, it should be between 1 and 10. Less than 1 retention factor represent fast elution, and accurate determination of retention time is very difficult in such cases, while high retention factor means slow elution. If value of capacity factor is equal to 5, then amount of analyte in the stationary phase is 5 times than in the mobile phase at a given point in the column. Thus, capacity factor K dash is related to the distribution coefficient of the analyte. Therefore, capacity factor K can be represented as ratio of adjusted retention time and dead time, which can also be written as mass of analyte in stationary phase and mass of analyte in the mobile phase. The amount and concentration are related by volume, so it can be expressed as ratio of ms by mm, which is equal to K into Vs by Vm. K is distribution coefficient and Vs and Vm are the volume of analyte in the stationary phase, and Vm is volume of analyte in the mobile phase, and ms and mm are the mass of analyte in stationary phase and mass of analyte in the mobile phase. Further, capacity factor can be expressed as K beta. K is distribution coefficient and beta is the volumetric phase ratio. Volumetric phase ratio can be defined as the ratio of volume of stationary phase and volume of mobile phase, Vs by Vm. So the retention factor for any analyte increases with the distribution coefficient between the two phases as well as the volume of stationary phase. The separation of two molecules A and B on the column is expressed by selectivity factor alpha. So alpha is defined as ratio of capacity factor of B and capacity factor of A. If molecule A elutes faster than molecule B, then the selectivity factor is always greater than 1 and vice versa. Factors affecting column efficiency. Martin and Sinch suggested a theoretical model of chromatography which divided the chromatographic columns into theoretical plates and plate number. They explained theoretical plates as an equilibrium partitioning of solute between stationary phase and mobile phase, while the theoretical plate numbers are indirect measure of width of a peak at a specific retention time. The column efficiency is determined by plate number N and plate height H, and that can be represented as N is equal to L divided by H, where L is the length of column. Large N and small h represent greater column efficiency and narrow analyte peak. Basically, column efficiency is a function of column dimensions, and these column dimensions are diameter and length of a column. Therefore, plate height and plate number H and N can be expressed numerically as H is equal to LW square divided by 16 TR square. L is length of the column, W is width of the column, and TR is retention time. Therefore, this formula can be rearranged again for N. N is equal to 16 TR divided by W square. So again TR is retention time and W is width of the magnitude of the base of a peak. N has no unit. For highly efficient column, N can be as high as 1 lakh and corresponding H can be as small as few micrometer. Columns with high plate number are more efficient than the columns with lower plate counts. Ideally, a solute elutes as a symmetrical Gaussian peak, and this behavior arises when the partition coefficient K of a solute is represented as concentration of solute in stationary and mobile phase. K is equal to SS divided by SM, where SS and SM are the concentration of solute in stationary and mobile phase respectively, and K is same for all the concentration of the solute. If an elution does not follow this trend, then the chromatographic peak will be asymmetric in shape. Another important factor that affects column efficiency is band broadening. The band broadening occurs when sample passes through the column. This can be explained by rate theory, which defines the shape of chromatographic peaks based on the possible paths available for the sample to elute out of the column. Some of the molecules pass through the column quickly due to their inclusion in the mobile phase, while others lag behind as they are accumulated in the stationary phase. This results in a Gaussian-shaped chromatographic band with widened velocities around the mean value. Thus, the width of peak increases as analyte moves down the column because of the enhanced space for broadening. Another important factor which affects band broadening is eddy's diffusion. In eddy's diffusion, there is the different path which is taken by a molecule to pass through the column. So in this case, peak broadening is due to different paths of different length taken by a analyte, and this phenomenon is known as eddy's diffusion. We have already discussed eddy's diffusion which affect band broadening. Another factor is longitudinal diffusion. Also, the analyte concentration at the edges is lesser than at the center, due to which it diffuses out from the center to the edges, resulting into band broadening. And this phenomenon is termed as longitudinal diffusion. In case of high velocity of mobile phase, analytes spend less time in the column and decreases the effect of longitudinal diffusion. We have already discussed two factors which affect band broadening. One was eddy's diffusion and another one was longitudinal diffusion. The third factor which affects band broadening is resistance to mass transfer. The analyte takes time to equilibrate between stationary and mobile phase of column. If the analyte has strong affinity for stationary phase and the velocity of mobile phase is high, then the analyte in the mobile phase will elute faster than that in stationary phase, and this can lead to band broadening. The band broadening is directly related to the velocity of mobile phase. Thus, the peak shape is affected by the rate of elution of analyte. The factors which are affecting our chromatographic separation can be avoided if we take a right concentration of the sample. Overloading of the sample can cause problem. The size of tubing should be small and column should be well packed. If column is not well packed, then the particles will take multiple path length and again affect the chromatographic separation. And stationary phase particles should also have narrow size distribution. Too long and too wide tubing should not be used because again they can bring about peak broadening. And if there is a longitudinal diffusion, then longitudinal diffusion can be avoided by using higher mobile phase flow rate. If flow rate is less, then diffusion is more. So you can keep your chromatographic separation to get a good resolution by using small size of tubing, by keeping the right concentration of sample, having a well packed column, and then narrow size distribution of resin and short tubing. And if all these parameters are satisfied, then you can get a good chromatographic separation. The Van-Demeter equation is used to relate the variance per unit length of a column to the linear mobile phase velocity. So here HETP, which is height equivalent to a theoretical plate, is equal to E plus L divided by V plus RV. E is eddy's diffusion, L is longitudinal diffusion, and V is average velocity of the mobile phase, and R is resistance to the mass transfer. Therefore, Van-Demeter equation describes the relationship between plate height and length, and which is a measure of column efficiency. The Van-Diemter equation is governed by three cumulative terms, which is eddy's diffusion, longitudinal diffusion, and resistance to mass transfer. A loss in peak efficiency can be observed as a wide analyte band, and therefore these three terms can also be viewed as factors that contribute to band broadening. Two more things affect the chromatographic separation, and these two are fronting and tailing. In fronting, if you have loaded more sample, there will be a fading of peak in the front, and then there is a steepness. So this is known as fronting, and then fronting can be avoided by less loading of the sample in a column. Another important feature is tailing. In tailing, your compound get attached to the sites in the stationary phase, and if it is attached, then what will happen? You will get a good Gaussian peak in the beginning, but in the end you will get a tailing kind of thing, a stretched peak. So these two phenomena also affect the separation process. So these to avoid this, there should be less overloading. Sample should not be overloaded, and the stationary phase should be chosen in such a way that your substance do not go and bind to the stationary phase. The ideal chromatographic separation is affected by fronting and tailing. What is fronting? Fronting is fading of a front of a peak and steepened tail, and this happens because of overloading of the sample. So overloading of the sample should be avoided to get a good resolution. Tailing is some sites on the stationary phase retain the solute more strongly than other site, therefore you get a strong tail in the end of the peak instead of getting a Gaussian peak. So fronting and tailing could result into poor separation, and these should be avoided when somebody is performing chromatographic separations. Resolution of a chromatographic separation is defined as the capability of a system to resolve one analyte peak from another. It is the ratio of difference in retention time of two peaks, which are retention time of A and retention time of B, TRA and TRB, to the mean of their base width, base of the peak width, WA and WB. And it can be represented by the formula given on the screen. R is also affected by alpha, column efficiency, as well as capacity factor. So resolution can also be given by the formula which is given on the screen, root of n divided by 4 into alpha minus 1 divided by alpha into 1 plus capacity factor of B analyte divided by capacity factor of analyte A. So root of n divided by 4 is efficiency, alpha is selectivity, and capacity factor is retention time. Therefore, the selectivity factor alpha can be manipulated to improve separations by changing the mobile phase, by changing the stationary phase composition, by changing the column temperature, and by changing the distribution coefficient to get a good Gaussian peak instead of merged peak. In prepared chromatography, the mixture of substances which are to be separated is spotted on the paper, and then it is developed by organic solvent. The molecules which has got more solubility in the organic solvent, according to the solubility they get separated. So analytes get separated, and then they can be visualized by different stains. And in paper chromatography, it is usually used for monitoring the reaction process. The chromatographic separations can be separated into various types based on the principle used for the purification of analyte. And some of the common categories of chromatography are as follows. First one is paper chromatography. Paper chromatography, you use a absorbent paper which is used as a stationary phase, and suitable liquid solvent is used as a mobile phase, and it is developed to separate different analytes. Thin layer chromatography utilizes silica as a stationary phase and mobile phase is organic solvent. The proteins or peptides which are to be separated or molecules which are to be separated are spotted on the silica, and then once they are spotted, they are developed by organic solvent. And depending on their RF value, they are moving forward in the silica gel. And once their movement is stopped, once organic solvent has reached at the top, you can take this out, you can dry it, and then you can spray it with different stains like iodine can be used for peptides, and then spots can be visualized. And on the basis of their RF values, you can know how peptide has migrated. So this technique, thin layer chromatography, is routinely used in peptide synthesis where you want to see the reaction process, whether peptide has been made or not, and it has been also used for routinely for seeing the separating the molecules which are small peptides or other small molecules. Thin layer chromatography is commonly used chromatographic technique in synthetic chemistry, and it is used for determining the purity of small molecules and also for identifying the progress of reaction. This technique compared to other technique is much faster and it requires very small quantity of the analyte to be separated. Ion exchange chromatography utilizes charge property of the analyte to be separated and the resin. So this can be divided into two parts. One is cation exchange chromatography and another one is anion exchange chromatography. In case of cation exchange chromatography, the positively charged analytes are binding to the negatively charged your gel. And in case of anion exchange chromatography, positively charged analyte are binding to negatively charged resins. So on the property of charge and charge-charge interaction, the proteins or any other compounds can be separated by ion exchange chromatography. Ion exchange chromatography is based on the charge-charge interaction between the analyte and charges on the resin. It can be further divided into two parts as cation exchange chromatography and anion exchange chromatography. In cation exchange chromatography, the positively charged analyte are binding to the negatively charged resin, while in case of anion exchange chromatography, the negatively charged analytes are binding to positively charged resins. Gel filtration chromatography is also known as size exclusion chromatography. As the name suggests, size, in this the compounds are separated on the basis of their size. The resin is chosen in such a way that some compounds will come out of void volume, means they will not enter the resin, they'll come out through the mobile phase, so they'll be coming out first. So larger molecules are coming out first in gel filtration chromatography, and smaller molecules, since they'll be entering the pores, so they'll be coming out later. So this will separate larger molecule first and then smaller and then the smallest. So on the basis of size, your molecules or analyte can be separated by gel filtration chromatography. In gel filtration chromatography, the column has to be very large so that separation is efficient. Gel filtration chromatography is also known as gel permeation or molecular exclusion chromatography. In this chromatography, the separation is simply based on the size of molecules. It lacks any attractive interaction between the stationary phase and solute. The pores of the resin are normally small. The larger molecules flow through the void space, therefore they are eluted first, while the small molecules enters the pore of the gel and therefore they are eluted late. And that is how the small and large analyte which are to be separated get separated in gel filtration chromatography. Affinity chromatography utilizes the property of affinity of an analyte towards a ligand, and then that ligand is immobilized on the resin. So once if that ligand is immobilized on the resin, so only compound which has got affinity towards that ligand will get absorbed on that column. So rest of the substances which do not have any affinity will come out during washing. So it is also shown in the picture that purple color compound has affinity towards the ligand, so it is fixed on that affinity column, and rest of the compounds like blue color or red color compound which do not have affinity towards that ligand is coming out in the washing. And substances which are adsorbed on the column can be eluted by different concentration of substances by this. In this, one of the example is antigen and antibody complex. You can immobilize antibody of certain substance, and then you can pass your antigen which is to be separated. So antigen-antibody complex can be separated by affinity chromatography. This is one of the example of affinity chromatography. Affinity chromatography utilizes the specific interaction between analyte molecule and the one immobilized on stationary phase or resin. The analytes are separated on the basis of their affinity towards the immobilized ligand on the resin. High performance liquid chromatography, which is known as HPLC, is an advanced form of column chromatography in which elution of analyte is carried down by applying high pressure. In this chromatography, the column is attached to a solvent delivery pump and the sample is injected automatically through auto sampler, and the fractions are collected on fraction collector and they are detected, and result can be monitored directly on the system. Reverse phase chromatography is used to separate proteins and peptides on the basis of their hydrophobicity. So this technique has gained importance for high resolution separation and analysis of biological molecules using hydrophobicity of the molecules. These are the application of chromatography. You can purify proteins as well as small molecules by chromatography. You can routinely apply chromatography in industry to purify large amount of individual components from complex mixture. It can also be used for quality control to monitor quality of food, water, soil and air. And chromatography is routinely used in research. It is used for purifying proteins, peptides and other small molecules. In pharmaceutical industry, it is used for the analysis of medicinally important molecules. Now let us summarize this module, what we have taught in this module. Chromatography is a separation process which uses phenomena of adsorption. The factors which are affecting chromatographic separation are distribution coefficient, mobile and stationary phase, column temperature and concentration of sample. Common type of chromatography which we have studied in this module are ion exchange, gel filtration, affinity, HPLC and reverse phase chromatography. Then we have also studied application of these techniques in research, pharmaceuticals and quality control.